So I'm recording the session. Hope that's okay with everyone. So today's session will essentially focus on how to build a classifier for images. And what we're trying to do is, if we get an image of, let's say, a cat, then we should categorize it as a cat. If we get an image of a dog, we should categorize it as a dog. And first we are going to build our own neural network with a convolutional layer, and after that we'll use a model called VGG16, which won the 2014 ImageNet competition. So ImageNet data is so that competition considered the main competition for images, and this is the model that won in 2014. So we'll take that, and that model can work on, you can categorize 1,000 different kinds of categories. So we will change that to categorize just 2 categories, which is cats and dogs. So to begin with, we have our usual libraries. NumPy is used everywhere. We're using Keras. So Keras is the main. There's sort of 2 popular frameworks right now. There is Keras, which can work with TensorFlow and Microsoft Toolkit and some others. So Keras and TensorFlow, all these are from Google. And the other framework is PyTorch, which is from Facebook. So from Keras, we're importing some more things. Under models, we'll be building sequential models. So essentially, neural networks are a series of layers, and we'll be adding layers to the model in a sequence. So that's why it's sequential. Then we'll be using a couple of activation functions, mainly something called softmax and relu. In terms of kinds of layers, we're using dense and flatten, where dense means all the nodes are connected to each other, and flatten is used after a convolutional layer. And then for optimizers, we are using Adam. So essentially, optimization can be thought of as trying to reach the bottom of a valley, where in the vertical plane is the objective function, and in the horizontal plane are the parameters which we're trying to optimize. And Adam is, so I'll back off a little bit. So essentially, in most of supervised machine learning, all that we are trying to do is we have something that we're trying to predict, and we use a bunch of algorithms to predict that. So there's a label which we're trying to predict, and there's a prediction which the algorithm provides. The distance between these two is what we're trying to minimize. So if we're trying to predict the price of a house, and the household price is 200K, then we want something as close to 200K. If we are trying to predict a category class 1 or 0, then we want the prediction to be close to 1 and 0. And we have algorithms to minimize that. And those algorithms have parameters which need to be optimized. So the most popular algorithm used to be stochastic gradient descent. And Adam is a little twist on that. I'll have a separate talk someday explaining stochastic gradient descent and its variations of momentum and RPS and how they are included in Adam, and why Adam is sort of more popular algorithm with neural networks. Does that sort of sound okay? Does anyone have any questions?
No.
Okay.
So far, so good.
Okay. In terms of metrics, so we are sort of using metrics for two things. One is when we tell an algorithm to minimize the distance between the prediction and the actual label, we need to tell the algorithm how to measure that. And there are various ways to measure it. The way that we're using right now is called cross entropy. And in case somebody is familiar with logistic regression, that also uses the same. Then there's some pre-processing stuff, normalization. We'll be using a convolutional layer. For graphs, we'll be using matplotlib. For metrics, to see how the algorithm has done, we'll be using the confusion metrics. So these are just the usual libraries. These are the paths. So essentially, we need 3 data sets: train and test and validate. So we discussed these 3 last time. Would anyone like to share what these 3 data sets stand for? Why we like to use 3 data sets?
One is for training the model.
Correct.
And the other one is for validations, because model is trained for a data set, and if it overfits itself, so to find out how whether it has overfit, we use a validation set. And the third one is for testing.
Very good. So the first 2, as was just said, was that Vijayashree?
It's Divya.
Sorry, Divya. Thanks, Divya. So as Divya said, one data set is for the model to train on, but the model can overtrain itself on a certain data set and learn peculiar behaviors of that data, which does not generalize to the larger population. So let's say if we give it some houses of a small block in, let's say, San Diego, it learns some things about proximity to beaches, and that'll be helpful for that block in San Diego, but it won't generalize to the whole of the country which doesn't have beaches. So we have training set, then the model also predicts on the validation set, and using those 2, we sort of optimize the algorithm. But because we're using both of them to optimize the algorithm, even the second data set somehow is influencing the optimization procedure, and that also ends up overfitting a little bit. So we have a third set which is the final and the test set, which we use very few times, like 2 or 3 times, to make sure that the performance of the model on the test, validate, and train is more or less similar. There's always some difference, but more or less similar. So do you guys have this data structure and the Jupyter and on your laptop set up?
Can you please share that folder with me?
Sorry.
Gmail, no? So, maybe I'll just forward it to you.
Okay.
Or you can just copy the link on Skype.
I might, I'm not sure if I have Divya's email ID. I'll need to add that to the.
Divya, do you have a Gmail ID?
Yeah, I sent it on Skype just now.
Okay. So hopefully everyone has that. If not, please ping me and I'll add you to the folder. So this is sort of the structure that is required by Keras for training models related to images. So here we are just creating these variables that will be used to essentially go to this path. So these are the 3 paths that we had just created. And all we're saying is that the images are 224 by 224 pixels. And the classes are dog and cat. And then we're saying to the image generator that whenever you pull images in the training data, we want you to pull 10 images at one time. For validate, it's 4, and for test, it's 10. So if you just run this piece of code.
Avneet, here.
Yeah.
The folder name is dog and cat, correct? The picture itself doesn't have any labels.
Correct.
So is that the way to set up? Every image we have to label and put in a different folder and then call it as a class. How does this know which folder this is? No question. Classes.
So
60, 100 images, huh? 79 images, huh?
So essentially the folder structure has folders and the folder names are classes.
The classes, that's how we set it up?
Correct.
Okay. So this will look, whatever we mention in classes, it's going to look for that folder?
Mm-hmm.
Okay. And it always has to have the same image size. Huh? Is that 224 by 224 pixels?
Correct.
Okay. And there's no count on that one, right? So one is 10. So why did he say batch size is 10 and 4 and 10?
So when it just pulls the data using these variables, it'll pick 10 and 4 and 10.
Okay, so
You can have it any way you like it. It should just be a divider of the actual number of images in that folder.
So I have very few images. No, I don't think there are 800 images, right? Is that the same thing you're passing through, or is it a different data set? Oh, I see. It is loading. Fine. So there are 800 images in that one, in the training data set.
Hmm.
Okay, fine. Sorry, I just saw only 79. I assumed there's 79.
No, it's great that you pointed that out. I had encountered them myself. So I just assumed the code was giving the right number, but it's always good to validate. So then we can just use this function and get some images and plot them to see what they look like. So here this function is essentially saying get me the next 10, because we had told it every time you pull, the batch size should be 10. So it pulls the 10 and it stores images and labels in these variables. And if you use the same and you run that, it'll just plot them. So here 1, 0 means a dog, 0, 1 means a cat. So it's sort of randomizing how it pulls the data. So you'll see different dogs and cats, but the labels should remain the same. Is that working? Does that sound okay?
Yeah.
Nice. So essentially, as of now, what we have is we have a directory structure under which we have sort of 3 directories of train, test, and validate. Under that, we have the 2 categories with the labels cats and dogs. And underneath, we have the images. And we've set that up so we can pick a certain number of them in a single iteration.
How
So
did he create that, this one, Navneet? Just can you look at that for a little second? How did he create that matrix of 1 zeros and 0 ones?
So it's creating labels based on the folder structure. So it realizes that there are 2 categories. So because there were 2, it is giving value of 1 to one label and 0 to other. If there were, let's say, 4, then it would have created 4 labels where each one of them would have, let's say, 1000 or 0100 or 0010 and 0001. So these are called as one hot encodings. So a lot of places to represent a category in machine learning, they use one hot encodings where the vector will be full of zeros and there'll be just one in there to represent that particular category.
But how do we create that one hot encoder? I mean, if it's 4, it's going to be 1000, right?
Mm-hmm.
Not 1, 2, 3, 4. Correct?
Correct.
How
So
do we
this
do that?
this is creating this code is creating it for you. It's creating the labels.
Train batches. That's it, huh?
Yeah.
Train batches, huh? Wow. Okay.
Okay. So the next step. So there are essentially 3 steps that we will always use when we are building models in Keras. So the first step is where we define the architecture, which is how many layers there are, how many neurons in each layer, what kinds of neurons, what kinds of activation function. So that is the first step. The second step is where we define the optimization algorithm. We define the loss function for that optimization algorithm, and we define the metric that we use to get an understanding of how well the algorithm is working. That's the second step. And the third step is actually giving it the data and asking the algorithm to figure out the weights to minimize the loss function over the predictions, between the predictions and the labels. Does those 3 steps sound okay? Okay.
Yes.
Great. So let's talk about the first step, which is how do we set the architecture? So essentially we will have 3 layers. First is a convolutional layer. Second is a flattened layer. And third is a dense layer. Now, convolutional essentially is so this is sort of the key thing behind convolutional neural networks is that you have layers of these, and the convolutional layer tries to find features and images. So if you're trying to figure out between cats and dogs, it might try and find features about, let's say, whiskers of cats, or what the eyes look like, or how the stripes of the furs are on cats. So those kind of things is what the convolution layer tries to learn. It might try to learn edges, or in case of birds, it'll try to figure out what's the typical shape of the feet of a bird. So each of those layers will try to learn something different about images and then use that information to make its decision. So in this case, the convolutional layer has a kernel of 3 by 3. I'll have a separate, I'll come to this another day in a more theory class, which shows how convolutional networks work. But just to keep in mind, it's a 3 by 3. So it's that 3 by 3 matrix, which is called the kernel of the layer, is learning some pattern. So if the pattern is whiskers, it's learning in that layer. If the pattern is the feet of a bird, it's learning in that matrix or the kernel. The activation function is ReLU, which is the main activation function that we will see in deep learning. Mainly So one of the key things about deep learning is that neural networks have been around since the 60s, but optimizing them was a difficult problem. And there were some breakthroughs, there were some learnings, some knowledges that helped figure out how do you build a model with millions of parameters and optimize it. So ReLU was one of them, and we'll talk about it someday as to how that helps. The input shape is, so the image is 224 by 224 pixels, and 3 means it's on red, green, and blue. So it's essentially a 3-dimensional matrix. So that's the convolutional layer. And that's mainly, these are the layers that do most of the magic for image analysis. Flatten is just to convert all that information into a single flat vector. And final is dense. Dense just means that all the nodes are connected to all the nodes of the other layer. And activation function softmax. So we'll also talk about softmax, but essentially softmax, what it does is it takes the score and it says e to the power that score divided by sum of e to the power score of all the categories. So essentially it converts scores into probabilities and it tries to give maximum weightage to the category which had the maximum score. That's sort of the gist of it. So we pretty much always use softmax in the last layer. Do these 3 layers sort of make sense?
Yes.
Okay.
Yes.
Thanks. So the first layer in Keras always talks about the input layer. So that's what this was. Essentially, input shape is equal to this. That it's always the first layer in Keras which defines the input layer, which is describing the data that we're going to feed it in. So that was the first step, which is creating the architecture. So you can run that. And the next step is to compile. And we give it the optimization function, which is Adam. And as we had discussed, optimization is sort of like finding the bottom of the valley. So you're standing at a particular place in the valley, and you see where is the steepest direction, and you take a step in that direction. So now the question is, how long a step should you take? If you take too long a step, you may be jumping around quite a bit. If you take too small a step, you won't make much progress. So learning rate defines how big a step. And when you build algorithms, then this is something known as a hyperparameter. So there are a bunch of parameters where you try a whole different set of values. So you'll try, in this case, we're giving 0.0001. You can also try 0.01. You can try 0.1 or 0.00001. You can try a couple of values and see which one gives you the best results. Cross entropy is the loss, which we use to define the distance between what the algorithm should predict and what it is actually predicting. And accuracy is, so this is from the previous class. Can anyone share what accuracy stands for? So for simple example of 100 data sets, and the algorithm, so we have 100 data points, and we're trying to predict the categories of 100 data points, and the algorithm predicted correctly 90 of them. And what's the accuracy?
90.
Correct. So the accuracy is 90%, or in terms of numbers, 0.9. So that's the where we define what algorithm to use, what loss function to use, and how to measure what algorithm is doing. And the third step, so last time we had used the function fit. We said model.fit. In this case, we're using fit underscore generator. That is because the data sets is essentially images, and it's going to pick random images from the folders. So it's a different function for that. We're giving it the folder related to train batches. So we have 800 images, and we told it to take 10 images in each iteration. So now all we're doing is we are taking the total number of images, which is 800, and dividing it by 10. So essentially what's happening is that what you will be doing is when you're standing in the valley and you're trying to take a step, then there is one possible way which is called stochastic gradient descent, where every time you look at an image, you take one step. There is another method called batch gradient descent, where you look at all the 800 images and you take one step. And here this is called mini batch. So you take, in this case, you look at 10 images and you make one step. And the thing is that if we take a step at each image, then you'll end up making a lot of random steps. If you only take a step when you look at all 800, the steps will be really good, but you're making very few of them. So this is sort of something in the middle, where you look at 10 images and overall you'll end up taking 80 steps to cover the 800 images. Does that sound okay?
Okay.
Yes, sir.
So as Divya had pointed out, we have for the algorithm a train batch and validation data. So here we are mentioning the validation data. And for validation, we had given 4 as how many images it'll pick in each step. And there were total 16 images. So we divide 16 by 4 and we get 4 here. Number of epochs. Does anyone remember what an epoch is?
It runs 5 times to fit the model on the same data.
Perfect. So one epoch is going through all the data one time. So here the epoch is 5, meaning we go 5 times through the entire data set. Purpose is just how much information we want the algorithm to give out. So here you can go ahead and run that. And what you will see is the accuracy is close to 0.5. What does that mean?
So it has just started with 50%.
Sorry?
It was right 50% of the time.
Correct. So, as you mentioned, the accuracy is 50%, so it was right 50% of the time, which means the algorithm is doing a pretty bad job. So that's sort of one of the takeaways, that figuring out the right architecture to build image models, figure out the categories of images and finding out those categories inside images is a very difficult task. So one way around it is to take a model that has done pretty well on images in general, hopefully images similar to what you're working on, and you use that model and you keep most of it and just change the final layer. So the final layer defines the categories you're trying to predict. So if you just change the final layer and then you retrain them, you freeze all the other layers that were already in the model, and you give this new model with the new final layer your data, and you tell the model to just learn the weights on the final layer. Does that sort of sound reasonable? So I'll just repeat that once. So that's essentially what we're going to do here. Actually, first we're just quickly going to test these images. And sorry, I jumped ahead. Let's first test images, and then I'll come back to what I was mentioning about transfer learning. So we had one folder for test images. So you can run this piece of code and you can look at what the test images are. And here, all it's doing is, it's basically saying we have test labels in this vector form, which is ones and zeros. And what we are going to need is to convert them into a single number. So all it's doing is it's saying take all the values and only pick the 0th column. So that converts this vector of 1 and 0 each to just one number, where 1 now stands for dog and 0 stands for cat. So all we are doing is we are figuring out the labels, and the way it figures out labels is it gives a one hot encoded vector of zeros and ones. In this case, we have two categories. So the vector has two values, where one of them is 1 and the other is 0. So we are converting that into a single number, that's all, which is required for calculating our accuracy metrics and the confusion metrics. So all it's doing is it's just picking the 0th column. So 1 0 here became 1, 0 1 in the second image became 0, and 1 0 again for a dog became 1, and so on. Does that sound okay? Does anyone have any questions?
No.
Okay. So now basically are taking that model and ask using the same using the function predict generator. So previously we were just using predict in images. It's predict generator, and we're just saying go to the test batch, get some data, and give us predictions. So it is giving these predictions of 0, 1. So here, which animal is 0, 1?
Mm-hmm.
So this one is a dog. This is labeled as 1, 0. And this one is a cat, labeled as 0, 1. So essentially the predictions it is giving is of a cat. So this model is taking every image and it's classifying it as a cat. And since half the images were cats and half the images were dogs, so we got accuracy of 50%.
What the steps mean here?
So step is basically, so when we initialized, let me go to the top. So that's a very good question. Here we set test batches, and we had said in each batch there should be 10 images.
Okay.
And this folder has only 10 images. So we can only take one step.
Okay.
If it had 100 images, then we could have taken 10 steps. So we took one step, we got the 10 images, and we got the predictions for that. And it predicted dog for all of, sorry, cat for all of them. So the next step is to get metrics around the model to see how it performed on the test set. Like we had used last time, we use sklearn, which is scikit-learn. We use metrics from that, confusion matrix. And we'll use cpon and matplotlib. These are the two main libraries for graphs. And as I'd mentioned last time, cpon makes prettier graphs, but its syntax is slightly difficult to figure out initially. Matplotlib is easier to figure out initially. Its graphs are not as pretty. You can make them pretty, but that requires a little bit extra work. So now we create a confusion matrix using the test labels and the predictions. Let me check in. I think somebody just messaged something. No. Okay. So here we are just creating the confusion matrix. So I'll revisit the confusion matrix at the end, and I'll go through it again like we did last time as to what's going on. I think it'll be more interesting to look at the VGG model, and then I'll revisit the confusion matrix at the end. Is that okay?
Okay.
Okay.
So coming back to the VGG model. So this, so there's a competition called ImageNet that essentially had a whole bunch of images, and this is sort of the interesting thing. They would have competition every year, and they would try to improve upon it. And for decades, there was no major improvement on the accuracy. And then deep learning started, and all of a sudden there was huge level of accuracy. And now I think the algorithms are more accurate than humans in categorizing the images. So the 2014 winner was VGG16, so it's a relatively old model. And so the whole idea of transfer learning is that this VGG model has about, let's see, it has 138,357,544 parameters. So this is a huge model. And if you look at the last layer, it's predicting 1,000 different categories of images. So essentially, this model has learned a lot of things about the images that were fed into it. So it has probably learned how to find edges. It has probably learned what the texture of cotton is like, what the texture of, let's say, marble is like, and so on. So there are all these basic common facts about images. They have now been learned by this model in all the layers that it has. I think it has about 23 layers. So now what we want to do is, given that somebody has created a very good model, we want to use their learnings, all the features that they have already learned, and just remove the last layer. So in this case, the last layer is this, predictions. So this layer is basically predicting 1,000 different categories. So we just pop that layer out and we put our layer in of 2 categories. Apart from that, what we'll do is this entire model, which has all these 130 something parameters, 130 something million parameters, we are going to freeze them exactly how they are. So this entire model we will freeze exactly as it is, because it has already done its learning, where it has figured out all the features that it needs to learn about the images that helps it to categorize images in different ways. So we'll freeze all that. We don't need to change anything. We will just change one layer, which is the predictions. And here there are 1,000 categories. We replace that by 2 categories. And we'll tell it to learn just the weights of that layer. So it's important to sort of understand this concept. Does this make sense?
Yes.
Awesome.
How do you know there is a cat and a dog?
Sorry, please say that again.
How do you know there's a cat and a dog in the images for the VGG16?
So right now, I don't know what the 1,000 categories are. I'm assuming cats and dogs are not in them. I'm just making that assumption. So right now the model knows certain 1,000 categories, and the model has learned features to predict those 1,000 categories. So at this point in time, the model does not know a cat or a dog, assuming that they're not in the 1,000 categories. We will make it learn what's a cat or a dog in the code in the next few lines.
But isn't that what we didn't do? We are not going to make it learn, no? The last layer has been removed, correct? So we are only using updating the prediction. The weights of the remaining layers will not be changed.
Correct. So essentially, the let's say the weights of the previous layers have learned uh, different kinds of shapes like circles and triangles and different kind of textures, what's
Fine.
furry and what's less furry, and
Mm.
what do paws look like in different shapes of eyes and noses and so on. Let's say those are all the features in the previous layers of the model, and the last layer is essentially adding up all those features to predict various categories.
Okay.
So that is sort of the assumption, and that may or may not be a fair assumption, but that's the assumption that we're making right now, is that all the previous layers have learned basic facts about categorizing images. And the last layer is focused on how to add all those features up to predict the categories.
Okay.
Okay. Thanks for bringing that question up. I think that's a very important question because this is just one way of doing it. You can also try not freezing it, and it'll probably just take the weights that it has learned as initial starting points, and it'll allow them also to change. So it's possible that so those can be two different strategies. One strategy is freeze everything and just change the last layer weights. The other strategy is to freeze some of the initial layers and allow changing some of the end layers. And another strategy could be to just allow changing everything. So whatever strategy works for you uh, is what strategy you would want to take. Currently, all we're doing is just
Can we do this though? This has got a lot of variables, no? We should try that. Can we run this entire model on the 800 images we have? I think it'll fail.
so. I mean, we can definitely try that, and we have code to try that. So there's a place I'll show where we freeze the layers. If we don't freeze them, then it will try to optimize everything.
It's
I'm
going to try to predict 138 million parameters weights.
correct. It will try to learn new values for all those weights based on the images that we're providing it.
Okay.
It'll take quite a while though.
Mm.
So, and that also brings me to another point, which is uh, so most of the optimization is sort of done in parallel. So we're actually running multiple operations at a time, which is why we take batches in the optimization. So instead of one data point, we take multiple, and all of them are solved in parallel. So I'll come to the point where we freeze the parameters. But the first step is Keras provides you a set of models. So the first thing that we're doing is we're just saying, go get the VGG model 16 and save it in this variable. So if you run that, then it'll go to GitHub and download this model. And then when you do the summary, so the summary will show you the architecture of the neural network. And it's essentially showing the input layer, which was 224 by 224 pixels and 3 for red, green, and blue. And then it has some convolution layers and doing some max pooling. All these we'll discuss later. But essentially, a whole bunch of convolution layers, max pooling, finally flattens them out, and 2 dense layers, and then just the final predictions. So maybe one thing else that you might try, as Sendhil was pointing to, was you can just optimize the final dense layers, all 3 of them, instead of just one. Essentially, you can try various approaches and see what works best for you. So here everything is already trained, and total parameters are 138 million plus change. So here, if you look at what kind of model it is, we notice that this is not a sequential model. So here they use the functional API for Keras to create this. So all we're going to do is we're going to convert this into a sequential model. So all I'm doing is initializing a model which is of the type sequential. And then VGG is nothing but those 23 or so layers. So we go through those. As long as it is not the last layer, we just add it to the model. So all we're doing is we take the VGG model and we take each layer and add it to our model, except the last layer. So now if you type model type, you get sequential, so which is what we're looking for. And now if you do the summary, then it doesn't have the final prediction layer. And the total number of parameters have also changed. So all we did was we told Keras to get us the VGG16 model. We created our own sequential model, and we copied all the layers of VGG to our sequential model except for the last layer. Does that sound okay? Does anyone have any questions?
No.
Okay. So here is the freezing part. So here essentially you're going through all the layers and you're saying trainable is equal to false. So you're freezing all of them. So this is where you can make changes. You can comment this out completely and the whole model will learn new parameters. Or you can go through, you can so you can see the number of layers in there and you can just say freeze the first 20. So the last 3 it won't freeze. So you can learn there. So this is the part where you can decide, do you want to freeze everything from the previous model, or do you want to freeze nothing, or do you want to freeze, let's say, the initial fundamental features? Because the way it works is in the first few layers it'll learn things that are more fundamental, more simple, like lines and circles and so on. In the final layers it'll combine those lines and circles to figure out this is the face of a bird, this is the face of a dog, and so on. So you can freeze the initial layers and unfreeze the later layers. So you can play with all those things. So this is the part of the code that will allow you to do that. Does that sound okay?
Yeah.
Yeah.
So now what you want to do is to add your final layer. So as was in this model and the previous model we created, it's a dense layer. It has two categories. VGG had 1000, so we are putting 2. The activation function is softmax, so that will give you probabilities for each category. So we add this, so you can run this part of the code. And if you run that, then if you run model.summary, now you'll see at the bottom you have this new dense layer, and this has 8194 parameters, and the model is showing these are the trainable parameters. That sound okay?
Yeah.
So now we have the same 3 steps of building the model. So what are the 3 steps? Number 1, we create the architecture. So that we just did. Number 2, we define the optimization algorithm and the loss function and the metrics. And number 3, we train the model on the data. So this number 2 is the same as the previous model, and this number 3 is also the same as the previous model. So here we see the accuracy now. This is for the training data after 5 epochs. So you can run this. It took me, I think, 10-15 minutes for the whole optimization, if I remember correctly, but depending upon your machine, it'll take you different amounts of time. And this is the accuracy on the validation data. So essentially what we see is that previously we were having accuracy of 50%, and now we have accuracy close to 100%. So that is essentially the power of transfer learning. You take the best model out there and you copy everything that you like, and just the last few layers you train on your data. That sounds okay?
Yeah.
Okay.
So can it recognize anything other than cats and dogs? Same thing? Same KGG, VGG?
Sorry, say that again?
Can it recognize? Can we use the same thing for recognizing any other object?
So we can run any image through that, and it'll end up giving a prediction of a cat or a dog. If it's close to a cat or a dog, then hopefully it'll give a score that's close to what the score should be for a cat or a dog.
Car and a truck?
So it'll definitely give a score. It may not be that meaningful, but if a car or a truck looks more like a cat or a dog, it'll end up giving some score.
Oh, so the VGG was trained on cat and dogs, huh? Is that what it is?
So the one that we have retrained, that,
oh no, the original one.
The original one.
Yeah. So if I can remove the RAS step just like you did and make it train on a car or a truck, it'll be able to do that.
Correct.
So all we need to do is remove the last layer and keep making it recognize the new one.
Correct.
Okay.
And as you had pointed out, you may also want to try unfreezing more layers and see how that goes.
Okay.
So this is just the same code as last time, where we now take this new model, which we built on top of VGG to predict cats and dogs, and we test it on our test data. So here is just getting those images and those labels. We plot them, and it's showing cats and dogs, where cats are 0 and 1, dogs are 1 and 0. We convert those into single numbers of 0 and 1. We then get the predictions. So these are the scores. And then we convert them into ones and zeros by explicitly saying if you're above 0.5, then you're 1, otherwise you're 0. So once we have this vector, because that's the format that scikit-learn expects, we take the labels, we give the prediction class, we have the confusion matrix, and then we plot that. So this is the confusion metric. So now we'll discuss what this matrix is telling us. Then I read it the same thing again. There is some randomness that you'll find in here. It's only 10 images in a test data set. So there's some randomness around the predictions. So that's why the accuracy will change. But in the previous one, it was giving 70% accuracy. Here it's giving 90%. So just to go through the confusion matrix again. So on the x-axis, we have the labels that were predicted. 0 for cats, 1 for dogs. And the true labels are on the y-axis. So 1 for dogs, 0 for cats. The diagonal axis is what was correctly classified. So 0, 0 meaning the label was 0 and the prediction was 0. And here 1, 1 meaning the prediction was 1 and the label was 1. So 9 out of 10. So we have accuracy of 90%. But this part is a little random. If you run it multiple times, you'll get different accuracies. And for that, we'll have to increase essentially the training set for the data and the test set for the data. But the gist of what we're doing is the same, which is they are essentially these layers called convolutional layers. And those layers learn basic features of images. So what we did today was we first built our own neural network with a very simple 3x3 convolutional layer. That was a very simple model, and these images are very complex, so it couldn't learn much. So then what we did was we used the concept of transfer learning, where we took a pre-existing model, we used Keras to import that model, and we used all the features and all the convolutional layers where it had learned the basic facts about images and how to predict the categories. So we took all those features. We just replaced the final layer. So the VGG's final layer was to predict 1,000 different categories. We replaced that to predict cats and dogs, and that created about 8,000 new parameters. We trained them, and then we applied them to our dogs and cats, and we saw that we got much better results than our original model. So that's the overall learning for today. Do you have any questions on that?
Are there any other model apart from VGG that you tried?
So there are definitely lots of other models. So each year, ImageNet will have a competition. They should have winners for each year. Sorry. Let me quickly see if I can find. Okay. So VGG is 2014. Then Google had another one which was better. This is the benchmark for humans. So this was an Indian researcher who works here. He spent a couple of hundreds of hours. He trained himself on how to do image categorization, and he did the best he could, and he was like 95% accurate. But then ResNet did even better than him. So this is when somebody who was trained to categorize images was beaten by a neural network. And then 2016 was Google. There must have been more after. I think they stopped ImageNet and now it's been done at Kaggle. But to answer your question, yeah, there are better models than VGG available. So VGG is 7, that's the accuracy, about 93%. And Google Net V4 is like 97% or so. I think that's what these numbers mean, if I'm not wrong. So yeah, there are better models that you can use. Any other questions?
Nope, that's great, Amit. Thank you.
Awesome. Thank you for your time. And if you have any more questions, please ping me. If you have any feedback on how I can make this better, I'm still learning to do this right. So please do let me know. Thank you and have a nice weekend.
Thank you. Thanks a lot. It was a very enriching session. Thank you.
Awesome. Thank you.